Okay, we're ready to start chapter 7. So here we go. 7.1 Estimating the population mean mu when you know the population. Standard deviation sigma. All right. Focus points explain the meanings of confidence level, error of the estimate, and critical values. Find the critical value corresponding to a given confidence level. Compute the confidence interval for mu when sigma is known. Interpret the results. And we want to be able to, if I move this up here, compute the sample size, the last part of section 7.1. Computing sample size. All right, right from the video, given a sample size n of 2.25, a sample mean of 8,200, population of the standard deviation of the population 750. A confidence level. We are 95% sure that mu, the mean of the population, is between 8,102 and 8,298. If you recall back in the video, when we have a large confidence interval, all right, we can be very, very sure that what he says is, I am 100% sure that the average age of everybody on the planet is between 0 and 200. Well, between 0 and 200 is a huge confidence interval. When the interval is large, you can be very confident, yeah, that the average age falls between that. Now, what if I make that between 50 and 55? Well, I'm not so confident that the average age of everybody on the planet is between those two numbers. All right. X bar. What we're doing is we're taking a sample and we're taking the mean of that sample. We're going to use that to come up with a confidence interval for the mean of the entire population. All right. We assume that my distribution is normal. And if it's not normal, if it's somehow skewed, the sample size has to be bigger than 30. Don't sweat this. This will always be into play. All right. Because of time and money constraints, difficulty in finding population members, and so forth, we usually don't have access to all the measurements of an entire population. We very rarely have that. Even if we did, the time it would take and the money to interview everybody would be phenomenal. It just wouldn't be worth it. In this section, we develop techniques for estimating the population mean mu by using some sample data. But we've been doing that since day one. This is what we do. We take a sample, we investigate it, and then we make some call on the entire population. We assume the population standard deviation sigma is known. Well, that's a little iffy. So you're telling me here, I don't know the mean of the population, but I somehow know the standard deviation. Well, to find the standard deviation, you'd have to know the mean. So what's happening here, he's easing us into this. All right. It's very similar to when we're back in section 6.2. Somehow the mean was exactly 0 and the standard deviation was exactly 1, standard normal. Well, that's not reality. Very few examples. Very few data sets have a mean of exactly 0 and a standard deviation of 1. But like I say, he starts us off by telling us, yeah, we know what sigma is, all right, which isn't, in actuality, it's not reality. So let's begin by listing some basic assumptions used in the development of the formulas for estimating mu when sigma is known. The estimate of a population parameter given by a single number is called a point estimate, all right? It comes in no great surprise that the mean of the sample is going to be an estimate for the mean of the entire population. We call that a point estimate. It's X bar, the mean of the sample. Even with a large random sample, the value of X bar, the mean of the sample, usually is not exactly equal to the mean of the entire population. The margin of error is the magnitude of the difference between the sample point estimate, the mean of the sample, and the true population parameter of the whole true population parameter, okay, which is mu. We've seen, during the election and we turn on TV, we see polling, and associated with polling is this idea of margin of error. They say, well, so and so is ahead, margin of error plus or minus 2 or 3 points. It says because surveys only talk to a sample of the population, all right, When these pollsters make phone calls, they're not talking to everybody, it's just a sample. We know the result probably won't match the true result. In fact, we found out in this election that some of the polling was way off, as it was back in 2016. The margin of sampling error describes how close we can reasonably expect a survey result to fall relative to the true population value. If you have a margin of error of plus or minus 3 points at a 95 confidence level, means that if we fielded the same survey 100 times, we would expect the result to be within 3% of this point 95% of that time. That's what a 95% confidence level means. If we did it 100 times, 95% of those would be within this margin of error, plus or minus 3 points margin of error. All right, so first we need to learn about confidence levels. The reliability of an estimate will be measured by the confidence level. Some of the most frequent ones that we use, all right, is 90% confidence level, 95% confidence. So sometimes we want to be 99% sure that we're close to the true population mean mu. Now, here's a case where we're actually drawing the normal distribution like we did back in chapter 6. You will not, repeat, not have to do this, all right, because I've kind of made this real easy for you. As we move on with the PowerPoint, you'll see what I'm talking about. All right, so let's assume we're looking at a 99% confidence level. All right, so 99% means, from a negative z-score all the way out to a positive z-score. This area represents the probability, 99%. So if this area in the middle is 99%, the entire area under the curve is equal to 1. If I take 1, subtract the 99, that's shared equally amongst these two regions, one to the very right and one to the very left. Well, taking 0.01, the difference between 1 and 0.99, dividing it by 2, I see that the area under both of these little sections is 0.005. Now, why would I need that? Well, the idea is I'm going to have to find this z-score. To find this z-score, all right, I need to find the area from this vertical line all the way to the left. Well, if this is 0.99, this little smidgen here is 0.005. If I put those two together, I come up with 0.9950. All right, so the area that's associated with this z-score is the area to the left, 0.9950. Now, 9950 is an interesting one because it falls right between 0.9949 and 0.9951. And if I follow my arrow down, the z-score that's associated with an area of 0.9950 is 2.575. All right, so you're saying, oh, I got to use the table. Well, not really. No, I'm just showing you how it would be done, pencil and paper. Now, if you go back to section 6.6, there are several times when the answer was considerably off what your calculator gave you. So if you wanted to be spot on, you still have to remember your tables and still, know how to find z-scores. But here's what I've done to help you out. These, if we were relying on the textbook, our textbook would have given us these very common confidence levels, 70, 75, and so forth, and it gives us the appropriate z-score. And what this does by me giving you this, it stops you or not prevent you, but does not necessitate you having to draw a curve, finding the area, go to a chart, and so forth. I've just flat out given you the z-scores. Not only that, for these, but over the course of times I've done this course, people have asked me, hey, what's the z-score that's associated with a 91% confidence level? And I take 91, subtract it from 100, that's 0.09, divide that, and then go through this whole process again. I've cut to the chase. I said, hey, if you got a 91% confidence level, you've got a critical value of a z-score of 1.70. Now, notice what I'm saying here. This is super, 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 super important. Please do yourself a favor, print this slide out because it has all the critical values. It has all these z-scores, and you're going to need these z-scores to compute the confidence interval. And then later on, when it comes time to find the sample size, the formula calls for your critical value, your z-score. So please do yourself a favor, print this slide out. All right. So we talked about error. All right. And we've seen this portion here, all right? The sigma divided by the square root of n. We saw this back in section 6.5 when you're working with multiple people. This is how you calculate the standard deviation. This z sub c, that's the critical value. That's these numbers here, 1.75, 1.81, all these values here. That's what this z sub c is called, all right? Critical values, the z-score. Now, to calculate the error, we're given the mean of the sample. The low end is we subtract the error, and on the high end, we take the mean of the sample and we add the error. And this gives us what's called a confidence interval. All right, so both these things, you're going to see in a moment or two that your calculator is going to be very nice to you. It's going to calculate everything you need to do, but I still need to show you how it's done pencil and paper. Julia enjoys jogging. She's been jogging over a period of several years, during which time her physical condition has remained constantly good. She jogs 2 miles per day. The standard deviation of all her jog times is 1.80. That's the standard deviation of the entire amount of times that Julia's been jogging over 2 years. During the last year, she's recorded her times. All right. She has a random sample of 90. She doesn't have all of them, just a sample. We're going to find the mean of that sample, which he tells us here is 15.60. So let mu be the jogging time for the entire distribution of all the times that she's ran for 2 years, or in fact over the past year, I should say. And we're looking for a 95% confidence interval. All right, 95%. This is what they want us to do. Could have been 90, could have been 98. They want 95 here. All right, so the first thing I'm going to do is calculate the error. All right, the error is the critical value, this z-score, which is associated with a 95% confidence level. Now back on my chart, 95% gave me a z sub c, or I'll just call it a z-score of 1.96. We're given sigma, and we know what n is. All right. So there's that 1.96. That's that z-score that's associated with a 95% confidence interval. He told us sigma, the standard deviation of all her running times over the last year, is 1.80. And she had 90 times, so n was 90. And your calculator will do this for you very nicely. All right, approximately equal to 0.37. But no problem doing that with your calculator. All right. So now what I need to do is to take this value on the left end, the lower end, subtract it from the mean, and then on the high end, add it to the mean. All right, so I'm taking the mean of, the mean of the sample of those 90 times was 15.60. I've calculated the error to be 0.37. So on the low end, I'm going to subtract it, and on the high end, I'm going to add it. This is something I've been given. This is what I calculated, the error. All right, so I come up with 15.23, between 15.23 and 15.97. If this was on an exam, the answer your calculator would have given you, or doing it pencil and paper, will be exact. So we conclude that with a 95% confident that the interval between 15.23 and 15.97 is the one that contains the population mean for all the times that Julia's been jogging. All right, 95%. What this means is, to be 95% confident, if we took 100 different samples, all right, of size 90, all right, 95 of those samples would fall between 15.23 and 15.97. That's what it means to be 95% confident. 95 out of 100 would actually fall between the true population mean, would fall between those two numbers. So pretty darn good. All right, so what I'm saying is the calculator bails you out, and at a new menu, we're going to go to stat and go to test, and then go to z interval. All right, this is a picture of what's going on here. please do yourself a favor, watch this YouTube video. I use these same values, but I actually show you how to find the Z interval. All right. We go to stat, then go to test, and come down to number 7. The good thing is you'll find out that there's no difference between the 83 and the 84. Make sure when you download your PowerPoint, you watch this video. I do this example live, so to speak. All right, here's an example here. He's asking us, suppose X is a normal distribution. Sigma is given to us as 6. We have a random sample size N of 16, a sample mean of 50. He wants us to construct a 90% confidence interval. Now, back on these here, some textbooks, 9% use this value 2.58. I should have blocked this out like I did on the previous slide. We're not going to use 2.58. Whenever you're given a 99% confidence interval, you need to use a z-score of 2.575. I should have blocked this out. This is not relevant here. I blocked it out on the previous slide. All right. So doing it pencil and paper, we want to be 90% confident. We want, this represents 90%, anything in this area here. Well, what's left for the two sections in yellow, so to speak? Well, if this is 90%, all right, there's 10% left, but it's divided equally amongst these two little sections. Half of 0.10 is 0.05, so 0.05 here, 0.05 there. But the key thing is to find this z-score, z sub c. The area that's associated with that is from this vertical line all the way to the left. If I take 0.90 and I add 0.05, that's what I get, 0.9500. Now I'd have to go to my table, but here again, this is an unusual one because 0.9500 falls halfway between 0.9495 and 0.94. I think it's going to be 50. Anyways, this is one that's given to you. Right, the area that's the z-score that's associated with 0.9500, there it is. It's 1.645. All right, so there's my formula to construct the confidence interval. I take the mean of the sample. I subtract the error on the low end, and then I take that mean. Same thing. I'm given the mean of the sample, and I add the error. Now, right here is the little formula he's using to find error. And what he's doing is letting his calculator do all the work here. All right. There's the z-score that was associated with a 90% confidence interval, 1.645. We saw that right here. There is 1.645. We're given the standard deviation of the population, 6, and we know where my end value is 16. All right, so all of this comes out to be 2.468. I subtracted on the low end from 50, the sample mean, and I added on the high end. All right, so we're 90% confident that the mean of the population falls between these two numbers. If I did 100 samples, 90 of them, all right, 90 of them would fall, the mean would fall between, the mean of the population would fall between these two numbers. 90% means 90 out of 100. If you did it 200 times, it'd be 180 and so forth. All right. So that one there, I didn't use the calculator for. I just did it pencil and paper. All right. No, I take that back. Here it is. It's the same one. It's the same one. Yeah. So I did use the calculator. My bad. I was messed up. So we did it pencil and paper. How would you do it in the calculator? You go to stat, you go to test, come down to number 7, Z interval. Now, the video shows you, it says input. Are you inputting data, raw numbers, or are you inputting statistics? Well, he's giving us sigma x bar. He's giving us statistics. Make sure you arrow over and press enter to let the calculator know you're using stats, not data. And all you're doing is entering in the numbers. All right, you're giving this, you're giving that. Now, for a C level, I put in 0.9, which is the same thing as 90, 0.90. And in the video, I talk about if you have a 90% confidence interval, the calculator actually lets you input the number 90. So you can use 90, you can use 0.9 or 0.90, whatever you use, it's still going to work, which is interesting. All right, and I've got this set up to 3 decimal places, and it gives me my interval 47.533. Well, I'm off by 1/10,000th. This is 52.467. This is 52.468. So really, 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 really close. So all that being said is there was no really need to do it pencil and paper because your calculator bailed you out. All right, number 12, same sort of thing. We're given sigma. Somehow we know the standard deviation of the population, but we don't know the mean of the population. I question that. Sample size is 36, and the sample has a mean of 20. I'm not worried about checking the requirements. All he's saying here is to construct a 95% confidence interval. All right. So once again, here's the formula. All right, and we're looking at a 95% confidence interval. My z-score there that's associated is 1.96. All I'm doing is in place of sigma, I'm substituting a 9, and then in place of n, I'm substituting 36. All of this, all right, works out to be 2.94. It's going to be the same thing on the other side. So I'm taking my sample mean, I'm subtracting that 2.94 on the low end, and I'm adding it on the high end. And here's my confidence interval between 17.06 and 22.94. All right. That one there, did I do? No, okay. Apparently, this one here I'm asking you to do on your own because I didn't do a sample of this. Numbers 9 and 10. What happens here is I've actually done it out pencil and paper, so you can check the answers. Number 9, here's my confidence interval, and number 10, there's my confidence interval. All right, so what you're doing is 9 and 10, and even 25. If I'm not mistaken, 25 is one of the problems in the homework set. All right, so that's done out pencil and paper. You can actually check it with your calculator. This is helpful. Now, how you're going to use this, you're going to be a little creative. All right, there's no set problems. I'm just giving you this because you could conceivably use this to check your answer. All right, doing some basic algebra with this confidence interval. All right, I can actually solve it algebraically for x bar. It's going to be the upper limit added to the lower limit divided by 2. Algebraically, I can come up with a formula for error. It's the upper confidence limit, subtract the lower, divide by 2. Now, this may be helpful if you know the answer, but you don't know the mean or you don't know the error. Or maybe you've got an answer you want to check that answer agrees with the mean and agrees with the error. All right, what I'm saying here is let's assume that all you're given is the confidence. Well, here's the case we give you the mean, but let's assume you were just given the confidence interval and you wanted to find x bar, which he tells you, and you wanted to find the error. Well, to find the error, you would take the upper 22.387, subtract the lower, divide by 2, and you would come up with an error of, 1.2367. If you were not given the mean of the sample, but just the confidence interval, you could add the upper with the lower divided by 2, and it would give you 21.12. You see how it agrees with x bar? This is helpful. If you're not given x bar, you're not given sigma, but you're given the confidence interval. That's all you're given. Here's an example here. I give you the interval between 20.388 and 21.612. And I said, what, by the way, what was the error? Well, you say, well, I don't know. I'm not given that. Well, a way of finding out is taking the upper 21.62, subtract the lower, divide by 2, because algebraically it works out. And you know the error for this problem was 0.612. Now, if I asked you for the mean and I didn't give you anything but the interval, you could take the lower, the upper one, add the lower one, take that sum, divide by 2, and you would know that the mean is 21. This could be very helpful if you've got an answer to a question and you're saying, is this one right? You could actually work backwards and see if your interval gave you the right error and the right mean that was given to you in the problem originally. Just food for thought. All right. So what's going to happen is the calculator is going to find that interval for you. All right. You go to stat, you go to test, come down to number 7, pop in the numbers, and the calculator gives you, and the numbers will be spot on. No doubt about it. Just putting in some numbers. But here's the things I think about this. Now, if you're listening to me, you obviously are watching this presentation. The only way someone could really mess this up is they just don't flat out watch these voiceovers because it explains everything. It kind of just takes everything and just break it down. What are you doing? You're just putting in some numbers. We get to the last section of this. Now, we're not looking for a confidence interval. All right. We're looking for the sample size where your calculator bailed you out. Well, it's going to bail you out, but you're going to put in the right numbers. There's no set function to find the sample size. You're going to put some numbers in, your calculator will solve it for you. No big deal. In the design stages of statistical research projects, it's a good idea in advance to know what confidence level you wish and select the maximal margin of error you want for your project. Hey, do I want to be 90% sure? Can I live with 85%? Or do I want to be 99%? How you choose to make your decision depends on the requirements of your project and the practical nature of what you're working on. All right. What specifications you make, whatever specifications you make, whatever you make, the next step is to determine, hey, how big of a sample am I going to do? Is it 30 people I'm going to survey? Is it 100 people? Is it 250? All right. Solving the formula, all right, for error, and it enables us to come up with a formula to solve for the minimal sample size. What does that mean? This is the formula for error. All right. If I do some algebra, I'm not going to show you the algebra here, but you all had algebra 1 and algebra 2, cross multiplying and taking this error formula, solving it for n, I come up with this. All right. To calculate the sample size needed in order to be whatever confidence level you're looking for. You take your z-score, you multiply it times the standard deviation of the population, which is given to you, and you divide it by the error. In other words, all of these numbers, these two will be given to you, and whatever confidence level you pick, all right, you'll know the z-score because it's back on that chart that I gave you, 90, 87, 91, 92. So what I'm saying is all three numbers are given to you. All you got to do is input those three numbers, put it in parentheses, and make sure you square it. That will give you your sample size n. All right, so it's the same thing here. I'm reintroducing the formula. You've got to have this formula in your notes, obviously. There's no menu item that does this for you. You've got to input those three numbers in, this quotient here, and then square the fraction, square the quotient. All right, here's an example. A wildlife study is designed to find the mean weight of salmon caught by an Alaska fishing company. Preliminary study of the random sample of 50 salmon showed that the standard deviation was 2.15. How large of a sample should I use in order to be 99% confident that the mean is within 0.20 pounds? All right. So here's my confidence level, There's my sigma, and here is my error. It doesn't say the word error, but within 0.20, that means, hey, that's your error, within 0.20, either 0.20 above or 0.20 below. All right, so I know my three numbers. Now, back on that chart, for 99%, there's my z-score, my z sub c, that's given to me. If you want to be 99% confident, you're using your z-score 0.2575, not the 2.58. I should have crossed that out. There's your error. So all I'm doing is, here's my formula. There's that z-score that is associated with 99%. There's sigma. He gave me sigma. There's my error. He gave me this. So I'm putting in those three numbers. Here's my divide sign, making sure that this is in parenthesis, and I'm squaring it. Now, here is the only little hiccup here. Normally, if you are rounding off, you would say 769.2, you would round off to 769. With this, with finding sample size, you always, always, always round up to the next higher number. So even though this 0.2 is not a 0.5, I'm still going to round this up to 770. The only time I wouldn't round up is that if this number in the tens place was a 0. Anything else, a 1, a 2, a 3, a 4, 5, 6, 7, 8, 9, I'm going to kick it up to the next highest number. All right? No matter what that decimal is except for 0. We're rounding up, not off. All right, this one here we're asked to find. We want to find the sample size so that we're 95% confident. He gives us the standard deviation of 3. He tells me what my error is. I need this value 3. I need the error. And then all I need to do is find the z-score that's associated with a 95% confidence interval. All right, the error that's associated, the z-score that's associated with 95% is 1.96. I get that off that chart I gave you. I told you that sigma was 3. The error was 0.04. I mean, all you got to do is enter this in your calculator. Make sure you're squaring the quotient. 0.09, normally you would round down, but no matter what this is here, because that 9 would make this 10th digit a 1. All right, I'm going to kick it up to 217. The only reason I wouldn't do that if both these numbers were 0. That's the only time I would not kick it up. All right, another problem. We want a 90% confidence interval. I tell you what the error is. I give you all 3 numbers. Well, I don't give you this one here. You got to look up the z-score for a 90% confidence interval. But I'll give you the error. I give you the standard deviation. So there it is. All right, 90%. The z-score is 1.645. I told you what sigma was. I told you what the error was. And 15.59, kick it up to 16. Even though if that had been even a 1, I still would have gone to 16. Another one here, this Atkins weight program. There's the formula again. There's a z-score that's associated with a 95% confidence interval. There is your sigma and there is your error. And letting your calculator do all the work here, you round this up 6906.27. You round up to 6,907. Always kick it up. This one looks just like something coming out of an exam. I give you the margin of error. I give you the confidence interval. I tell you what sigma means. Just go to your chart, find out the z-score that's associated with 99%. 1.645 again, times sigma divided by the error. This whole thing squared, 209.55, rounded up to 210. All right, hope that helps.